Welcome back to another video in this series where I'm summarizing and providing code examples for the popular book Reinforcement Learning by Richard Sutton and Andrew Barto. In the last video, I gave a brief introduction to RL. In this video, I'll be covering Chapter 2, which discusses the multi-armed bandit problem. The multi-armed bandit problem, or K-armed bandit problem, is just a very simple version of a full reinforcement learning problem that's used to highlight the dilemma between exploration and exploitation, which I'll talk more about soon. The term K-armed bandits is analogous to a slot machine in a casino. They're called bandits because they're known to take people's money. So picture a slot machine, except instead of just having one lever or arm that you can pull, it can have any K number of levers. Taking an action is like pulling one of the levers, and each lever will give you some reward with some probability. The goal is to maximize winnings by learning which levers output the highest rewards with the highest probabilities and pulling those levers as much as possible. To formally define the problem, we can introduce some simple mathematical notation. Firstly, A of t is the action taken at time step t, or essentially which lever we choose to pull at time step t. R of t is the reward received at time step t. And Q star of A is the actual value of any action, A, and it's defined as the expected reward for taking that action. So we can read this as Q star of A is equal to the expectation of receiving some reward R of t, given that A of t, or the action taken at time step t, is equal to A. Remember that we don't actually know Q star, which is the value of each action. In other words, we don't know how much reward to expect to receive for pulling each lever. Because of this, we have to estimate the value of each action, and that estimation is represented by the QT of A, which is the estimated value for any particular action A at time step t. So the goal is to get QT of A to be as close to Q star of A for all actions. If we can get our estimates close to the true values of each action, then we can know which levers to pull to maximize reward. At any point in time, there will be one action whose estimated value is the highest, and we call this the greedy action. Choosing the greedy action is called exploiting, and this is because we are making use of the knowledge we have gained thus far to choose the action that we think will give us the highest reward. Choosing an action other than the greedy action is called exploring, and this is because we are trying a different action to see if we can learn something new. We might think a certain action is the best, but in reality, it might not be, and this is why exploring can help. Exploitation might maximize reward for one time step, but exploration could maximize reward in the long run. And the conflict between choosing when to exploit your knowledge of the environment versus when to explore the environment in hopes of gaining new knowledge is called the exploration-exploitation dilemma. And now that we understand the multi-armed bandits problem, we can start looking at how it can be solved. So our first solution to the multi-armed bandits problem are called action value methods. And action value methods are just a group of solutions that focus on getting accurate estimations of the value of each action and using these estimations to make decisions about which action to choose. So they're composed of two parts. Firstly is estimating the values of a given action. Secondly, selecting which action to take based on the estimated value of all the actions. So focusing on the first part, the simplest way to estimate the value of any particular action is to assign the value of that action as the average of the rewards that were received every time that action was taken. And we call that sample averaging. So this is the formal definition of sample averaging. QT of A is our estimate for the value of some action A at time step t. So we're assigning it to the average of the rewards that were received for previously taking this action, or the sum of rewards when A was taken prior to T, divided by the number of times A was taken prior to T. Mathematically, we can read this as the sum from I equals 1 to T minus 1, or from the first time step to the current time step of all the rewards that were received, multiplied by 1 if this one predicate is true. So the one predicate is just a simple predicate that returns 1 if the action selected at this time was A and 0 otherwise. And then we divide that by the number of times this action was taken, or the summation across all time steps of the one predicate if action A was selected at that time step. Now that we understand sample averaging, we can start looking at how it can be implemented in the multi-arm bandits problem. The simplest implementation of sample averaging would be to store the rewards for each action, as well as the number of times each action was taken. Then these could be used to calculate the sample averaging formula on the previous slide. The problem with this implementation is that the memory and computation needs grow as more rewards are seen. As we see more rewards, we would have to store more rewards, and the computation to sum up all of them would take increasingly longer. Instead, we'd like to avoid having to save all of the rewards to lower memory and computation needs. This can be done through an algorithm called incremental updating. The incremental update algorithm is pretty simple and is shown here. It can be read as Q of A is equal to Q of A plus 1 over NA times R minus Q of A. This means that we update the estimate Q for some action A by using its current estimate plus 1 over NA, where NA is the number of times this action has been selected, multiplied by the reward we just received for taking that action minus the estimate. I didn't show the mathematical derivation for this algorithm here, but it's shown in the book, and updating the estimates this way is actually equivalent to following the sample averaging algorithm we saw previously, that just sums up all the rewards and then divides them by the number of times the action was selected. The advantage of this algorithm is that it only requires the current reward instead of all the previous rewards that were received for taking this action. That makes it much more memory and computationally efficient. The incremental update algorithm can more generally be thought of as being in the form new estimate is equal to old estimate plus step size times target minus old estimate. And it's important to understand this general form because of a lot of the algorithms we're going to see in the future take a similar form. Remember that all we're trying to do is come up with an accurate estimate for how much reward a particular action will give us on average. When we take an action, we get a reward from the environment, and we can think of this reward as the ground truth for the value that for the value of that action, though it might be noisy, because in some environments, taking the action, the same action at different times can give different rewards. But once we get our reward, we want to update our estimate in the direction of the reward. That's why we call the reward the target, because we want to aim our estimate towards it. The term target minus old estimate measures how far away our current estimate is from the reward that was just received. So we can think of it as a measure of the error in our current estimate. Finally, the step size determines how much we want to move our current estimate to be closer to the target. Now that we know how to estimate the value of actions, we can move on to the second part of action value methods, which is choosing an action. There are two basic ways to choose an action. The first and most simple way is to use greedy action selection, which is to always choose the greedy action or the action with the highest estimated value. This can be thought of as always exploiting. The second method is called epsilon greedy action selection. In this method, we choose the greedy action most of the time, but choose some other action with some probability epsilon. and doing this ensures exploration. So epsilon could be any value of our choice. For example, if epsilon is equal to 0.1, we would explore 10% of the time and choose the greedy action 90% of the time. So in this method, we still exploit most of the time, but occasionally we explore other actions that may lead to better rewards. The final detail before we can implement a solution is to understand how we can initialize our estimates of the action values. The simplest way is to initialize them all to 0, and this works fine. Another way is to initialize them optimistically, which means to start them off with values much higher than they could ever be in reality. For simple averaging methods, whichever way we choose to initialize the estimations doesn't really matter in the long run, because the bias begins to disappear once all actions have been taken at least once. In the short run, however, optimistic initialization encourages exploration. With optimistic initialization, the first few rewards for any action are guaranteed to be below their estimated value. This forces the action that's the best action to constantly change, which forces the agent to try out other actions and encourages exploration. So with this method, greedy agents can be encouraged to explore in their initial phases, which increases the likelihood of them finding the true best action. Now that we know how to estimate the values of actions and how to select an action based on those estimations, we can combine these steps into a simple algorithm to solve the bandit problem. So in the beginning of the algorithm, we initialize the action value estimates and NA, or the number of times the action was selected, to 0 for all actions. Then we loop forever, and this algorithm is using epsilon greedy action selection. So with probability 1 minus epsilon, it takes the greedy action. That's what the argmax is doing. Argmax A Q of A just means take the action with the highest Q value. Then with probability epsilon, we choose to explore by selecting an action randomly. Then we get our reward by actually taking the action in the environment. And finally, we increment our action count and update our estimation for the value of this action using the incremental updating rule we went over previously. Now we can get into a Python implementation. So now I'll show a Python implementation of multi-arm bandits agent using the action value methods we just discussed. The link to all this code will be on GitHub if you want to take a look at it yourself. So first thing is this agents.py file where the agents are actually implemented. First is the generic multi-arm bandits agent class, which is pretty simple. In the initialization, it just initializes the actions as a list, and each action is stored in this action class, which is defined right above it. And the action class simply keeps track of the Q value, or our current estimation, and the number of times an action was selected for each individual action. And you can initialize any action optimistically, which just means that you initialize the Q value to a high value. Otherwise, the Q value starts off as 0. So going back to the multi-arm bandits agent base class, every agent has a select action function, which will be implemented in the child class, which I'll show in a second. That's why it's passed. Then it has different types of action selection. There's select action greedy, which is super simple. It just loops through all the actions that's in this self.actions list, and it finds the action with the highest Q value, and it selects that action. Then there's a select action epsilon greedy, which takes in a value epsilon, and it uses the Python random library to come up with a random number between 0 and 1. And if that number is less than epsilon, then we explore by choosing an action randomly. Otherwise, we choose to exploit by doing greedy action selection. Pretty simple. And that's the most important part, is the actual update of the Q value for any individual action. So this update action estimation function simply grabs the action and increments its n, or the number of times it was selected. Define the step size as 1 over n. This alpha we'll review later. And it updates the action's Q value based on the incremental update algorithm we showed previously. So it's the new Q value is equal to the old Q value plus the step size times the reward minus the current Q value. So that same algorithm there. Then there's two agents here. There's a greedy agent and an epsilon greedy agent, both of which are inherit from the multi-arm bandits agent class. So starting with the greedy agent, its initialization function is super simple. The super here just calls the parent class constructor. So it literally just means it's going to call the same constructor implemented here, which initializes the actions. And it passes in some environment, which I'll show in a second. Then it implements the select action function. So since it's a greedy agent, it just selects actions greedily, and the actual logic and implementation for that we already showed. Then there's the epsilon greedy agent, which also inherits from the multi-arm bandit agent class, does the same exact thing in its constructor. It calls the parent class constructor with the environment. The only difference with this is that when you're creating this agent, we also pass in some value epsilon, and when we're selecting an action, it selects the action epsilon greedily and passes that epsilon value there. So that's the implementation for these agents in Python. Super simple, but it'd be cool to actually see these agents performing in the multi-arm bandits environment, and we can do that. So there's a host of solutions, but the what I found is this GitHub repo here. Somebody implemented that allows you to easily run different versions of the multi-arm bandits problem. So you can pip install this repo or clone it however you like. I just pip install. So literally just pip install and then this string here, and that will allow you to use this repo locally on your computer. And we will take a look at two of the different environments that this repo provides. The first one, super simple, is called Bandit 2-arm deterministic fixed v0. So it's the simplest case where one bandit always pays and the other always doesn't. So the agent simply has to learn which bandit is paying, right? And then we'll also look at one that's a little bit more complex, which is Bandit 10-arm random v0, which is a 10-arm bandit with random probabilities assigned to both payouts and rewards. So there's 10 arms instead of 2, and each arm pays under some random probability distribution, and also that's it. So I can show how to use these in this test agents.py file. It's pretty simple. Start off by importing OpenAI Gym. If you're not familiar with that, there's a lot of documentation on that out there. Gym Bandits is the name of the GitHub repo that I just showed. And then from agents, that's this agents file that I showed earlier, we're going to import that greedy agent and the epsilon greedy agent. Don't worry about the other stuff. That'll come later. And then some matplotlib stuff so we can show some graphs. And then if you want to specify any of the environments, you can just uncomment them at the top here. So we'll start with that simple 2-arm deterministic fixed v0, which is the simple version of the multi-arm bandits problem where there's 2 arms, one pays out, one doesn't. We'll initialize some greedy agent with that environment and some epsilon greedy agent with that environment, and we'll use 0.1 for our epsilon value, which means that we will explore 10% of the time. And we will run this whole problem 10,000 times just so we can get a good average of how things are performing. And there's also some code for some matplotlib stuff here and some printing stuff. So if we want to run this, simply just run as I was saying, there's some code here for some matplotlib stuff and just some general printing. And if we want to run this, we simply run this Python and then testagents.py. That's the name of the file. We can run it like that. And we see here for the graphs that they perform, both the greedy version and the epsilon greedy version perform pretty much the same on the environment. And if you look in the console here at the bottom, you can see some printing. I think what's really important is the average rewards over the 10,000 time steps that we ran it. So you see that actually the greedy agent outperforms the epsilon greedy agent, and that's because the way that the greedy agent works is it's going to essentially just find the best action and stick with that action entirely, versus the epsilon greedy action occasionally chooses to explore, which causes, so even though it does find the best action, it causes its average reward over the 10,000 timestamps to be lower. Yes. So now we can also test out that more complex environment, which is the 10-arm random v0, which, like we discussed before, it's going to be a 10-arm, so it's going to be 10 bandit arms instead of 2, and each bandit arm pays out with a reward of a random distribution. So we can run this. And to really understand the results of what happens here, we need to run it multiple times. But basically, sometimes the greedy agent can actually outperform the epsilon greedy agent. Sometimes it won't. And it's basically depending on whether or not in the greedy agent's first pass of testing out all the actions, it finds it's lucky enough to find the best one. So in this case, it was lucky enough, and we can see here that it did outperform the epsilon greedy agent. But if we keep running this, it's another. Yeah, so if we keep running this, like for example, in this example, it wasn't lucky enough, and we see here that it performed way worse. It has an average reward of 0.12 versus the epsilon greedy agent, which has an average reward of 0.62. So it's a lot less stable. But like we discussed before, if you initialize the action values optimistically, then we can essentially ensure exploration of even the greedy agent, and it can perform consistently a lot better. And you can actually do that with this code super simply, just going to where we initialize our actions, changing this optimistic variable to true. And if we run that, we can see that the greedy agent will be much more consistently performing better and close to on par with the epsilon greedy agent, as we see. Now we've looked at the most simple version of the multi-arm bandits problem, so we can increase the complexity to take one step closer to the full reinforcement learning problem. Before we can increase the complexity, we need to understand the concept of reward distributions and stationary versus non-stationary rewards. Reward distributions are just a fancy way of describing the probability of certain actions giving certain rewards. Remember that the whole point of the multi-arm bandits problem is that there's some underlying reward distribution for each action that we do not know, and the goal is to learn the reward distribution so that we can select the best action and maximize reward. So far, the environments we've discussed have stationary rewards. Simply stated, this means that the reward distributions do not change over time, and any action would give out a reward with the same probability the first, 100th, and 1000th time it was selected. In reality, most reinforcement learning problems have non-stationary rewards, which means that the reward distributions change over time. The methods that we've learned so far struggle to handle this type of environment. For example, consider a simple 5-armed bandit environment in which one arm outputs a constant reward while the other arms output no reward. The only difference is that every 500 steps in the environment, the arm that outputs the reward gets randomly switched to a different arm. This would be an example of a non-stationary environment. Of the non-stationary bandit environment that I just described in Python. So it's super simple, just has an action space of 5, which means that there's 5 arms that can be selected. Every time the step function is called, we just make sure that a valid action is being called. Initialize the reward to 0, and if the action is equal to the best action, which at any point in time is the action that can output reward, then the reward will be 1. Otherwise, the reward will stay as 0. And then we keep track of this step count such that every 500 steps, we call this select new best action, which changes the reward outputting arm to some other arm randomly. Yeah, and that's pretty much it. And we can use the same test agents file previously and just make sure that the environment is set to the non-stationary bandit environment. And when we run the previous epsilon greedy and greedy agent on this environment over 10,000 steps, we can see that both of the agents do perform pretty poorly. The greedy agent scores an average of 0.14, and the epsilon greedy agent does perform better with 0.36, but 0.36 is still pretty poor. So it's showing how these two agents that we've defined previously aren't very good at handling the non-stationary case. The reason that the agents perform poorly when the reward distribution is suddenly changed is because their action value estimations are heavily based on rewards from an old distribution. In other words, their action value estimates are slow to change even though the reward distribution changed quickly. Recall the sample averaging method, which is used to update the action value estimations. Just q of n plus 1 is equal to q of n plus alpha times rn minus q of n, where alpha is going to be equal to 1 over n. So at the start of the game, the best action could be action 1, for example. Then 500 steps later, it could change to action 4. And then another 500 steps, it could change to action 2. So at this point, choosing action 1 would clearly be a bad action, but the sample averaging method would still rate it somewhat favorably. And this is because at one point in time, it was the best action. And the sample averaging method works by averaging all the rewards that were received from an action from the beginning. So we'd like to be flexible to a changing reward distribution such that when the distribution changes, we can quickly learn which actions are now good to take and which actions are no longer good to take. And one way to accomplish this is by setting alpha to a constant value between 0 and 1 instead of setting it alpha equal to 1 over n. And to understand why this works, consider what's actually happening when alpha is equal to 1 over n. So at time step 10, alpha is equal to 1 over 10, or 0.1. And at time step 1000, alpha is equal to 1 over 1000, or 0.001. And so the ability to change our estimation for an action diminishes over time because alpha gets smaller over time. So this means it can be difficult to change our estimation even if the rewards that an action give us changes. And the estimation can be heavily biased to the rewards that it used to give. Now consider the case when alpha is a constant value between 0 and 1, e.g. when alpha equals 0.9. So at time step 10, alpha would equal 0.9, and at time step 1000, alpha remains the same. So if an action that used to give a reward suddenly stops giving a reward, alpha will cause the estimation of that action's value to quickly diminish. Vice versa, alpha can also cause an estimation to quickly increase if an action suddenly starts becoming rewarding, and in this way we can quickly respond to a changing reward distribution. Constant alpha agent in Python in the same agents.py class that we looked at before. So simply the same thing, inherits from the multi-arm bandits agent base class. The only difference is when we're initializing it, we can pass in some value alpha. And then when we call update action estimation, we also pass that alpha to that function. And then in the implementation of that, you can see here alpha is received, and instead of using alpha as 1 over n, which it is by default, it'll use the alpha that we pass in. And we can test out this constant alpha agent here and compare it against the greedy agent and the epsilon greedy agent that we defined before on that same non-stationary bandit environment. If we run that, you can see here that the greedy agent and the epsilon greedy agent do pretty poorly on the non-stationary environment with average rewards of 0.24 and 0.31. But the constant alpha agent scores an average reward of 0.85. So it's able to actually adapt to that changing reward distribution as opposed to the other agents. Remember that action value methods are composed of two parts: estimating values and selecting actions. So we've just looked at a couple of different approaches for estimating values through sample averaging and also using a constant alpha. Now we can look at some other methods for selecting actions. The two methods we've learned for selecting actions thus far are greedy action selection, which is always choosing the action with the highest estimated value, and epsilon greedy action selection, which selects an action greedily most of the time, but chooses to explore some other action randomly with probability epsilon. Epsilon greedy marks an improvement over the greedy method, but when choosing to explore, it still chooses actions randomly. So is there a better way to select actions? We'll be exploring that next. One way to select actions could be to choose them with a preference for the actions that we are less confident about. For example, consider the case of moving to a new town and you're trying to find which restaurant has the best meal among some number of new restaurants. Greedy action selection would be like visiting all the restaurants once and then going to the one that satisfied you the most forever. Epsilon greedy action selection would be like acting similar to greedy action selection, except choosing to revisit one of the other restaurants occasionally. Maybe the first time you went to a restaurant, they didn't prepare the meal the best, but that's not how the quality is on average. That was just some bad run. But with epsilon greedy selection, you could discover this. Another method could be to choose which restaurant to visit based on how satisfying the meal was, but also with a preference for restaurants that you've tried less. For a restaurant that you haven't tried as much, you're less confident about the quality of food being good or bad. So you may want to experiment with it more to become more confident about its quality on average. This concept is called upper confidence bound action selection, or UCB for short. UCB can be formally defined with the formula in the top right here. This can be read as the action at time t is selected as the action that maximizes the formula in between the brackets. And for the formula in between the brackets, Q of A is the estimated, QT of A is the estimated value of the action at time t. And the right side of the equation in the brackets can be thought of as a representation of the uncertainty of what the reward will be for any given action. NT of A is the number of times the action has been selected. Since it's in the denominator, as it increases, it causes the value on the right side to shrink. This encapsulates the concept that as we select an action more, we become less uncertain of its value. ln of t denotes the natural logarithm of t, which is the current time step. And if you're familiar with the natural log function, then you understand that as t rises, our uncertainty increases, but slower over time, just like with the natural log function. And finally, the parameter c is some constant between 0 and 1 and can be considered as determining the degree of exploration. Higher c values can cause greater exploration because they cause the uncertainty about actions to be larger. Okay, so here is a Python implementation of a UCB agent. The init function is basically the same as the constant alpha agent. We can pass in the alpha for our constant alpha action value estimation. The only difference is we also now have this c variable that's used in the UCB calculation. The update action estimation function is the exact same. The only difference is the select action function, which is now different because it's going to select an action using that UCB algorithm that we just saw. So we're going to want to get these UCB values, or the UCB value for each action, and then we're going to return the action that maximizes that UCB equation, or the action with the maximum UCB value. So we iterate through all the actions, and we want to calculate the uncertainty, which is that right half of the equation. So if the action has never been selected, then our uncertainty is essentially just infinite. If it has been selected, then we use that right set of the equation, which is the c times the square root of the natural log of t over n. The reason we do it this way is because if the action wasn't selected, then n would be equal to 0, and then we'd be dividing by 0, which is bad. So we just return that infinite value. Yep, so once we calculate the uncertainty, which is the right side of the equation, we just add that to the action's Q value, and that is the UCB value for the action. And again, we return the action that has the maximum UCB value. So now we can test out our UCB agent for different values in this test UCB agent.py. Simply just run this file. So it's testing it for different values between 0 and 1. So 0.1, 0.2, 0.3, 0.4, and so on and so forth. So it seems like 0.1 is the best value for a UCB agent. Oh, I forgot to say this is on the same non-stationary environment that we were just looking at. And you can see, though, regardless of C value, actually, all of these values are around 0.98. And just to recall, the greedy agents were performing, I think, an average reward of under 0.2. The epsilon greedy agents were around 0.3, so they were performing pretty poorly. Then once we added constant alpha, we got performance up to around 0.85. And now with using UCB action selection, it's around 0.98. So it's performing really well, and it's able to really easily respond to that quickly changing distribution in the non-stationary environment. All of the previous methods for solving the multi-arm bandits problem thus far have been action value methods, or methods that work by estimating the value of actions and then selecting an action based on that value. To wrap up, we'll look at a whole new class of methods called gradient bandit methods. As opposed to action value methods that estimate the value of actions, gradient bandit methods don't care about the value of an action, but rather learn a preference for each action over another. This preference has no interpretation in terms of reward. Only the relative preference over other actions matters. The probability of selecting any action with gradient bandit algorithms is given according to a softmax distribution. If you're not familiar with softmax, it's a function that outputs probabilities over a set of numbers such that the probabilities sum to 1. In this case, the set of numbers are the actions. So each action will be given a probability of being selected, and the probabilities of all these actions will sum to 1. For example, if there's a game with 3 actions, then the probability of selecting action 1 could be 0.3, action 2 could be 0.6, and action 3 could be 0.1. The value ht of A represents the preference of selecting an action A over other actions. On each step, after selecting the action A of t and receiving the reward R of t, the action preferences are updated based on the shown formula. The top part of the equation, that's this part here, represents the preference update for the action just taken, and the bottom part of the equation, that's this part here, represents the preference updates for all other actions. Alpha greater than 0 is a step size parameter, and that determines the degree to which the preferences are changed at each step. And R mean at time step t, that's how this is read, is the average of all of the rewards from all time steps, including time step t, for an action A of t. Similar to previous methods, this can be updated using incremental updates with the sample averaging method or a constant alpha parameter that's better suited for non-stationary rewards. R mean of t can be thought of as a baseline against which the current reward is compared. If the reward is higher than the baseline, then the preference for the action is increased. If the reward is lower than the baseline, then vice versa. The bottom part of the equation moves the preferences for all other actions in the opposite direction. So after an action is taken, we observe the reward and update the preference for the action taken and all other actions, and then the next action will be selected based on the softmax formula in the top right that uses these action preferences. So the softmax formula is a softmax done over all these h of t values that are calculated for every action. So this is an implementation of a gradient bandit agent. So in the initialize function, we pass in the alpha that we want to use, which is the same alpha in the formula, and we initialize all the h values, all the preferences to 0. Then when we want to select an action, we want to run that softmax function, and we do that through this get action probability, this underscore get action probability function. That's essentially just running the softmax algorithm using the action preferences, and that's going to give us back the probabilities that we want. And then we select an action using a weighted random selection from those probabilities. So what that means is once we get the probabilities back, and maybe there's, for example, 4 actions, and the probability should be 0.2, 0.4, 0.3, and 0.1. Then we select an action using that probability distribution, and then we return that action. And I guess the other part of the gradient bandit algorithm is updating the action preferences. So first off, we update R mean, which is essentially the Q values. So we can do it the same way using the update action estimation function that we've used in previous agents. So we can, in this case, I just hard-coded the value 0.9, but you can use whatever value as like a constant alpha for R mean. It's essentially the same thing as the Q values in the previous agents. And then once we have R mean, we can do that calculation for reward minus R mean, and we're going to call that the error. And then for each action, we're going to want to update its action preference. But remember that there's a slightly different formula if the action is the current action that was just selected. So if it's AFT versus if it's not AFT, they have slightly different formulas for updating their action preference. So that's what this block of code is doing. But either way, we call this underscore update action preference function, specifying whether or not it's the current action. And we get the current action preference. That's what the h values of action is. And we get the action probability, which is that essentially what's returned from the softmax function we saw earlier for that action. So the probability of this action being selected is that action probability. And then once we have that, we can run the code to update the preference for the h value for any action. So if it is the current action, we set that new h value equal to the existing h value plus the alpha times the error, where the error is reward minus r mean, times 1 minus the action probability. And if it is not the current action, we set its preference equal to the existing preference minus alpha times error. Remember, error is reward minus r mean, times the action probability. And then we can test out the gradient bandit agent over 10,000 runs on the non-stationary environment, just like we did for the other algorithms. And once that finished running, so we tested it out for different values of alpha, all the way from 0 to 100. And we can see that we get pretty drastic differing results, but depending on what value of alpha we choose. But it seems like a value of alpha around 40 gives us the best performance on this environment, with an average reward of 0.91, which wasn't as good as the 0.98 we were seeing before for the UCB agent, but still pretty good. Or sorry, not for the UCB agent. That was the I'm blanking here. Yeah, oh sorry, that was for the UCB agent. But yeah, still pretty good performance of average reward of 0.91. Finally, we can summarize everything we've learned this chapter. The K-arm bandits problem is about how to balance exploration and exploitation to learn how to maximize rewards from actions that output these rewards from either a stationary or a non-stationary probability distribution. Action value methods are a group of solutions to this problem that focus on getting accurate estimations of the value of each action and using those estimations to decide which actions to choose. Sample averaging is the simplest value estimation method that uses the average reward received from an action as its value. Sample averaging can be implemented using an incremental update rule that is time and memory efficient, since it doesn't require storing rewards across all time steps. Sample averaging performs poorly on environments with non-stationary rewards due to its inability to adapt to changes in reward distribution. And to remedy this, a constant alpha step size can be used. Initializing the value estimations optimistically can encourage exploration. Greedy action selection always exploits by choosing the action with the highest estimated reward, while epsilon greedy action selection acts greedily most of the time, but chooses to explore another action randomly with probability epsilon. Upper confidence bound action selection is an alternative to greedy and epsilon greedy action selection that selects actions with a preference for uncertainty. Of all the methods shown in this chapter, UCB performs best on the K-arm bandits problem, at least the non-stationary version. And lastly, gradient bandit algorithms are an alternative to action value methods that focus on learning a preference for each action over each other instead of an estimation for the value of actions. The variations of the K-arm bandits problem we've seen thus far have been non-associative, which means that we haven't had to associate different actions with different situations. In non-associative tasks, the agent tries to find a single best action if the reward is stationary, or to track the best action over time if the reward is non-stationary. In general RL, there is more than one situation, and the goal is to learn a policy, which is a mapping from situations to the best actions in those situations. For example, consider if there were several different K-arm bandits with different reward distributions, and at each step, one is chosen at random for the agent to select an action on. You could try using one of the non-stationary algos we've discussed, but unless the true action values change very slowly, they wouldn't work very well. Consider instead that when one of the bandit tasks is chosen, you are given a clue about its identity. And now you can learn a policy, which is a mapping from identity to best action. This is an association search task, also called contextual bandits, because it involves trial and error to both search for the best actions and an association of these actions to the situations in which they are best. This is one step closer to the full RL problem, but it's still not there yet. In the full RL problem, in addition to learning an associative search task, actions are allowed to affect the next situation as well as reward, and we'll start looking at that in the following chapters. Thanks for watching.